Okay, let's kind of do some of each. All right, oh man, it's always like, so let's talk about derivatives for a bit, and then we'll circle back around to these limits to infinity, because I think even though you might not be there yet, you're going to get there eventually. So let's go ahead and talk about derivatives. Specifically, let's go back to, for a second, limit definition of the derivative. I recognize I'm going ahead of where you are in class. Okay. You're going to see this, and you're going to want to have seen it a few times because it definitely comes up again and again and again. So there's a couple different ways of writing this. My preference is to write it as, for some function f of x, we like to write that the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That's one way of writing it, but there are alternate ways of writing it. Specifically, let me look at this. I've got there's one way of writing it that I also like, but there's a different way. Yeah. So another way of writing this is the following. F of x is equal to the limit as z approaches x of f of z minus f of x all over z minus x. And these really are saying the same sort of thing. Let's look at a picture for a second. So the idea here is that, right, you've got your function, it maybe looks like this, and we're interested in finding the derivative at this point. I'm going to call this point x, f of x. And then we're going to look at some other point on the line. And we can either call this point z, or we can call it x plus h. And this point here is either z comma f of z, or if you prefer, x plus h comma f of x plus h. And so what we're doing is we're finding the slope of the line between these 2 points. One way of writing it is this way. The difference in the y's, f of z minus f of x over the difference in the x's, z minus x. Or one way is writing it this way. The difference in the y's, f of x plus h minus f of x over the difference in the x's, x plus h minus x, which is h. So both these things are saying the same thing. They're just a different way of expressing it. And really not even that different. In this way of writing it, we're letting h approach 0. If h approaches 0, this x plus h is getting closer and closer and closer to x as h goes to 0. Or writing it this way, we're letting this point z approach x. So we're literally writing the limit of z approaches x. So let's talk about why you might use one of these versus the other. So I'm always going to default to using this first expression. And the reason why is because it's algebraically less challenging to compute. Let me show you what I mean. Let's pick, so let's look at this example here. So let's say we want to use limit definition of the derivative to calculate the following. So calculate, find the derivative of words, f of x equal to, what do I got here? Yeah, let's say x squared minus 8x plus 2. And I'm going to do it in the less nice way first. So we're going to do it as the limit as z approaches x of f of z minus f of x all over z minus x. So we're just going to do it. We're going to plug in the z's, plug in the x's, and look what we get. So we're going to have the limit as z approaches x of z squared minus 8z plus 2 minus x squared minus 8x plus 2 over z minus x. Now, as is typical, it's a what kind of limit? It's a 0 over 0 kind of limit. These are always going to be 0 over 0. And to deal with the 0 over 0 type of limit, you have to deal with the 0 that's in the denominator, which in this case is the literal factor z minus x. We have to be able to manipulate the top so we can factor out the z minus x, which is more complicated, in my opinion, than factoring out an h. So this is why this is less nice. Let's see, working on this, we have the limit as z approaches x. I'm going to simplify. I'm going to get z squared minus 8z minus x squared plus 8x. The 2's cancel all over z minus x. Oh, or on the top, you mean right here? Thank you, yeah. Sorry, it's z squared minus 8z minus x squared plus 8x. I have to try and factor out a z minus x from the top. That's, oops, pressing buttons accidentally. It's never a good idea. So here's what I know I need z minus x to factor out. So I'm going to just do that. But really, it's kind of a pain in the ass. Yeah, really, it's kind of a pain in the ass. So I'm going to write this as, sorry, as z approaches x. I know that if I have a z squared minus x squared, I can factor out a z minus x from that. And I have a minus 8z plus 8x. I can write that as a minus 8 times z minus x. And then from the z squared minus x squared, I can write that as the limit as z approaches x of z minus x times z plus x minus 8 times z minus x over z minus x. And then from each of these, I can factor out a z minus x. There are probably other ways of getting there. This is just the way I happen to see it. I'm left with a z plus x minus 8 all over z minus x. And then I can finally cancel that with that. So then I can take the limit as z approaches x of z plus x minus 8, and throwing in x for z, I get x plus x minus 8, which is 2x minus 8, which is what the derivative of x squared minus 8x plus 2 is equal to. And again, I would point out, this seems terrible. I didn't like doing that. It is much easier, in my opinion, to do it the following way. So just as a comparison here, we could have done this. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h, which is going to be the limit as h approaches 0. Let's see, f of x plus h is going to be x plus h squared minus 8 times x plus h plus 2 minus x squared minus 8x plus 2 all over h. And then we're just going to simplify. So we get the limit as h goes to 0. We have x squared plus 2xh plus h squared minus 8x minus 8h plus 2 minus x squared plus 8x minus 2 all over h. And then all the not h things get to cancel out. The x squared and the minus x squared, the minus 8x and the plus 8x, plus 2 and the minus 2. And then everything that's left behind has an easy to factor out h. We're left with h times 2x plus h to the first minus 8 h. Those cancel out. And then you're left with the limit as h goes to 0 of 2x plus h minus 8, which is 2x minus 8. So the point here is that it's almost, you don't have to think really. And I know we should want to think, like you don't have to think about what you're trying to do if you do it this way. We know that we're always trying to factor out an h to cancel h to the bottom. Whereas in this other way of doing it here, you really have to, in my opinion, do more mental work to try and actually get that z minus x to factor out of the top. So I really, really strongly recommend doing it this way if you are permitted to. I know in some people's classes, there are a couple homework problems where they ask you to do it this other way, which is totally fine. But in general, this is considered to be the nicer version of doing this. It's the easier computation. Sure. The hard way or the easy way? Okay. Let's try it. What do you got? Okay. Like that. All right. So let's see what we can do. So I'm not always good. I've not practiced doing it this way much. So I'm always like, well, let's see what we can do. So we're gonna find the limit h approaches 0 of, sorry, I just automatically, I can't even help myself. So I'm not gonna write, this is the way I would do it. I won't do it the other way. Like I would start off, if I was doing it the normal way. Sorry, normal is very judgmental. The easier way, I would do this. And actually, this is going to be a little bit helpful because it's going to help me see one thing. So I'm going to have 2 plus radical of 5 times x plus h minus 2 plus radical 5x all over h. And I'm not going to go any further with this, but I know that if I was trying to do this, I would cancel the 2's, and then I have a radical minus another radical, which means I would have to multiply by what? Right. So I'm pretty sure the other method I'm also have to multiply with the conjugate. So at least doing this will help me seeing that. So let's do it the other way, which is the limit as z approaches x. Some people use x approaching a, but z approaching x seems to be things that people are using, of f of z minus f of x all over z minus x. So let's take a look here. If the limit as z approaches x of 2 plus radical 5z minus 2 plus radical 5x all over z minus x. And right after that, again, we can see the 2's are going to cancel. So we're going to have the limit as z approaches x of radical 5z minus radical 5x all over z minus x. Welcome to those on Zoom. We're just doing some other definition of the derivative stuff where you do the other kind of harder to computate definition. And here we are going to multiply by the conjugate. So radical 5z plus radical 5x over the same thing. Cool. So then multiplying out the things that are conjugates, this might actually not be quite so bad. Might have made it out to be worse than it is. So let's see, we're going to get 5z minus 5x all over z minus x times radical 5z plus radical 5x. And then we can cancel it, or we can factor out a 5 from the top, and then the z minus x will cancel. So that's not too terrible. We have the limit as z approaches x of 5 times z minus x all over z minus x times radical 5z minus plus radical 5x. Z minus x is canceled, and we're left with the limit as z approaches x of 5 over radical 5z plus radical 5x. And then we plug in plug in x for z, and we get 5 over the square root of 5x plus the square root of 5x. In other words, we get 5 divided by 2 square root of 5x. Or if you prefer, 1 over 2 times 5x to the negative 1/2 times 5. And the only reason I've written it in this other way is to make it explicit that this is kind of still using the same pattern as the power rule. There's an extra little 5 in there, which we'll talk about later on. We'll talk about the chain rule, but it's good to see it this way. This is what we would expect the derivative to be. Let's look at one more example of this other way of doing it, because although it's not always fun, it is certainly doable. Let's look at something like, let's make it, we can go that way. We might do two more examples. Let's do one more example first. So let's try finding, to use the alternate definition to find f prime of x for, let's do this one. F of x equal to x cubed minus 2x. All right, so let's see what we've got here. F prime of x is the limit. I always forget, z approaches x, right? Yeah, z approaches, or whatever you like, but z approaches x of, z cubed minus 2z minus x cubed minus 2x over z minus x. And our job, when we're doing it this way, is to try to factor out the z minus x from the top. Right? Just like when it's the h version, you're trying to factor out the denominator from the top, you're trying to factor out h from the top, you're trying to factor out a z minus x from the top so you can cancel the z minus x. So whenever you're doing these limit definition of the derivatives, the denominator is always a problem. That denominator needs to get canceled out before you can kind of carry on. So let's see here. Okay. So we've got the limit as z approaches x of, yeah, I don't love that. So typically you want to group similar powers together. So I'm going to write this as z cubed minus x cubed. I'm also going to write this as minus 2z plus 2x. I guess I could have factored out the minus 2, but I didn't. I'll do it in the next step. So I can definitely look over here and see if I factor out a minus 2, I'm going to be left with z minus x. Great. That's right down here. We have the limit as z approaches x of, I'll leave this alone for a second. If I factor out a minus 2 here, I'm going to have a minus 2 times z minus x. And then z cubed minus x cubed, you can totally factor a difference of cubes. Z cubed minus x cubed is going to be z minus x times z squared plus zx plus x squared. It is worth knowing, just as a kind of quick aside, I feel like I've said this before. Have I said the acronym SOAP before? Okay, cool. Then I'm not gonna say it again. If you want me to say it again, I won't, but I'm gonna leave it that for now. So then we can factor out a z, you can either factor out the z minus x or divide each thing by z minus x. Okay, this divided by that's going to give you z squared plus zx plus x squared. And that divided by z minus x is going to give you a minus 2. And then plugging in z for x, we get x squared plus x times x plus x squared minus 2, which is 1, 2, 3x squared minus 2. As we would certainly expect to get if we think about the power rule. Questions? Yeah.
You could do limit of sine and cosine the same way, right? Z to dx.
You could, yeah. Well, I wouldn't say, yeah, the limit of z approaches x, sure.
It would just be a different way, but the utility would be the exact same answer.
I mean, the thing about using z and x for sine and cosine specifically is it makes it harder to use the sine angle sum rule, which is how we typically do this.
You would have to use a different identity.
Or rewrite the sine of z as something else. Like you write it as z minus x plus x.
That would be equivalent.
Yeah. But we're not right there, because before we talk about sine and cosine, I do feel like we should start to talk about the product and the quotient rule, because they are things that are coming your way soon. So just as a reminder, I know we've kind of gone back and forth, but I'm going to remind you all, we've definitely talked about the power rule. So for a function f of x equal to x to some power, we have shown that the derivative is definitely p times x to the 1 less power. It's definitely a rule that works for any power p, for any real number p. P could be 5, p could be a million, p could be a fraction, like 2/3, p could be a negative number. As long as p is a real number, this rule works. It's nice when p is an integer, it doesn't have to be. So for example, if your function is equal to, I don't know, something like x to the 7th power minus 6 over x to the 4th plus the square root of x cubed minus plus 6x to the 9th, we can totally use the power rule to differentiate this if we first do some simplifying. So I definitely want to rewrite this as f of x equal to x to the 7th minus 6 times x to the negative 4th plus x to the 3rd to the 1/2 is x to the 3/2 power plus 6x to the 9th. And then it is very straightforward to take the derivative using the power rule. Power rule is going to tell us that the derivative is 7 times x to the 1 less power minus 6 times minus 4 is plus 24 times x to the 1 less power. Power comes down, 3/2 times x to the 3/2 minus 1 is 1/2. And then finally, 9 times 6 is 54 times x to the 9 minus 1 is 8. That's how we differentiate something like that. functions being added together, subtracted together, we kind of just don't even pay attention to that. We just say, well, I'm going to take all the derivatives and then add or subtract it all together. Okay. Let's see here. Let's see if I have anything else important to say about that before I start moving along to the next thing. Oh yeah, I should say that. So for example, and I should say this in general, if you are differentiating something, it often pays to simplify it before you differentiate. There are lots of rules that allow you to do things like today we will certainly talk about the quotient rule, but I'm going to tell you for a function like this, f of x equal to, I don't know what I got here, or something like this, but not exactly true. 6x to the fifth plus 9x squared minus 7x plus 4 all over x to the fourth. You could use the quotient rule for that once you know the quotient rule, but you don't have to, and you really don't want to. So typically, if it is worth simplifying something to make it simpler, then we should. So first, simplify. I'm going to divide each thing by its denominator. So f of x is equal to 6x to the fifth over x to the fourth plus 9x squared over x to the fourth minus 7x over x to the fourth plus 4 over x to the fourth. And then I'm going to rewrite them each so they look like just something times x to a power. So I don't want something in the denominator because that's not very helpful. But if I have this is equal to 6x plus 9x to the minus second minus 7x to the minus third plus 4x to the minus fourth, then it is very, very easy to use the power rule again. So people kind of get jammed up by 6x using the power rule. Kind of like, well, it's just going to be 6. If you like, you can think of it as the 1 comes down and you get 6 times 1 times x to the 0th, but anything to the 0. So this is just going to be the derivative is equal to 6. And then 9 times negative 2 is negative 18 times x to the negative third. Negative 3 times negative 7 is positive 21 times x to the 1 less power is negative 4. And negative 4 times 4 is negative 16 times x to the negative 4 minus 1 is negative 5. So that's how we differentiate something. Simplify it first and then take the derivative instead of using the quotient rule. You totally could use the quotient rule here. We really don't want to. Sometimes you have, well, I should say, sometimes it makes the most sense to use the quotient rule, but you don't ever have to actually use the quotient rule. It's kind of cool. Yeah. Nope, you don't. There's a way to, so I would say you probably should use the quotient rule, but I will point out there is always a way to avoid using the quotient rule if you really want to. No, the way you avoid the quotient rule is you just rewrite it as, so for example, just to point out, and we'll get there later, but if you're trying to take the derivative of something like h of x over g of x, you can always rewrite that as h of x times g of x to the negative first. You have to use the chain rule, but you can always avoid using the quotient rule if you really, really wanted to. I'm not saying it's a good idea. I'm just saying it's possible. So yeah, but you're right. Typically, if your denominator is more complicated than just a single term, like you got some other stuff added or subtracted on, it is usually sensible to use the quotient rule there. Let's see. Speaking of these rules. Oh yeah. Oh yeah, I knew that. Yeah, there was. So I did want to talk about this. So let's say someone said on an exam, I want you to find the limit as h approaches 0 of something like 2 plus h to the fifth minus 32 all over h. I really don't want to multiply with 2 plus h to the fifth. And the thing is here, really what they want you to do here is to find this limit by recognizing, how can I spell? Maybe by recognizing it as the derivative of some function. Evaluated at some point. So the idea is that this looks like some limit as h approaches 0 of f of x plus h minus f of x all over h. That's the idea here. And our job is to kind of figure out, well, what is the function that they're actually using? Well, I see a really good clue. It looks like my 2 plus h is my x plus h. So if I had to think about this, I would say, okay, well, it looks like my f of x is probably something being raised to the 5th power. Because my f of x plus h is x plus, I guess I should say what x is. What is x here? Or my x is 2, right? So I'm saying my x plus h is 2 plus h. So I really should say f of x is x to the 5th. F of x plus h is x plus h to the 5th. F of 2 plus h is 2 plus h to the 5th. And it definitely looks like f of 2 is 2 to the 5th, which is indeed 32. Oh, things are starting to come together. So what this is looking like here is this is looking like the limit as h approaches 0 of 2 plus h to the 5th minus 32 all over h is looking a lot like the limit as h approaches 0 of f of 2 plus h. Right, that's my f of 2 plus h right there. Yeah, look, checks out. Minus f of 2, okay, all over h. And I know that that is the derivative of my function evaluated at 2. And now we can say, well, look, there's our function. What's the derivative of that function? Power rule, derivative of x to the 5th is 5x to the 4th. So if I know my derivative is 5x to the 4th, then I can say that my derivative evaluated at 2 is 5 times 2 to the 4th, which is 5 times 16, which is 80. That is certainly the intent of a problem like this. It's not to multiply out 2 plus h to the 5th. You totally could, right? You are all certainly capable of multiplying out 2 plus h to the 5th. It's just time consuming, right? We don't want to. Now, I will admit, I kind of took my time doing this one, but it is a faster way to see what's actually happening here, especially if the power is something much larger than the 5th power. For example, we could say something similar like, make something up here. Find the limit as h approaches 0 of, let's make it truly heinous here. Sure. 1 plus h to the 100th power minus 1 all over h. There's no way you're multiplying out 1 plus h to the 100th power. So our job is to say, well, this looks like limit h approaches 0 of some f of, I'm not even going to write x plus h, I'm going to write 1 plus h. So it's looking like some f of 1 plus h minus some f of 1 all over h. So your job, after looking at this, I want you all to think about and write down, I want you to identify what is your f of x. Write it down. Somewhat in order here. This. All right, so hopefully everybody came up with or was thinking something along the lines of my function is x to the 100th power. If I plug in 1 plus h to that, I can see that f of 1 plus h is certainly 1 plus h to the 100th power, and more important, well, as importantly, f of 1 is just 1 to the 100th power, which is just 1. So it totally works. You can say that, oh, great. So then this limit, that limit as h goes to 0 of 1 plus h to the 100th power minus 1 all over h is just f prime of 1. We know that f of x is x to the 100th. So f prime of x is 100 x to the 99th power. So f prime of 1 is 100 times 1 to the 99th power, which is just 100.
Should be a lot harder if f of x wasn't just one by. Maybe just f of x square plus x.
Right. It would be more, it's so it's definitely typically written in a way where it's not meant to be super duper hard to identify what the function is. Let's look at one more example. Got room. Let's say I want to find the limit. In fact, I want you all to try this one. So the limit is h goes to 0 of the cube root of 125 plus h minus 5 all over h. So you should be able to identify. So let me ask you all what, and write it down, don't say words. You should be able to identify what is f of x plus h, or maybe more easily, what is f of 125 plus h. That should help you think about what your function actually is. Here is the noise here. All right, so if I'm thinking about f of 125 plus h, I'm seeing that f of 125 plus h is just looking like the cube root of 125 plus h. So I'm really trying to think of this limit as the limit as h goes to 0 of f of something. And it looks like 125 plus h is my something plus h. And then it should be minus f of what? Right. We're trying just to kind of make it look like the limit definition of the derivative. So then if f of 125 plus h is the cube root of 125 plus h, then it does work out that f of x is just the cube root of x, and f of 125 is the cube root of 125, which is 5. So then things are looking good. This is looking like f prime of 125. It's the limit definition. It's f of the thing plus h minus f of the thing all over h, the limit of it. So then we just take the derivative. So this is x to the 1/3 power, and the derivative of that is 1/3 x to the negative 2/3 power. Just throw in the power rule at it. And so then this limit, as h goes to 0 of the cube root of 125 plus h minus 5 over h, is going to be f prime of 125, which is 1/3 times 125 to the negative 2/3 power. Which we would never leave like that because we can totally simplify it. That's going to be 1/3 times 125 to the positive 2/3, which is 1/3 times 125 to the 1/3 is 5. 5 squared is 25. So you get 1/75. And really, that's not entirely true. I was going to say, really, there's no other way to evaluate this limit, but that's totally not true. You could totally evaluate this limit in a very complicated, messy way that will totally work out, but it's a pain. Sure. You can. Well, I will say, yes, you can use the conjugate. But the conjugate of the cube root thing is a different thing than the conjugate of a square root thing.
Even if you like multiply by 1, the conjugate twice.
Well, so let me address your question with an example. So in fact, let's actually, I was wondering if I was hoping I like this one. So let's actually look at how do we find, so let's really kind of prove to ourselves that for f of x equal to the cube root of x, or x to the 1/3, we want to find the derivative using the limit definition, and we're going to do it the long way. So you may not want to write this down because it gets very messy. So we're going to find the derivative. I might not write this down really, but okay. So limit as h goes to 0 of f of x plus h minus f of x all over h. And the limit as h goes to 0 of the cube root of x plus h minus the cube root of x all over h. Okay, so I'm going to remind you of something I've already said today. So I'm going to write it out though, because it is worth remembering in case you haven't seen it before. So just so you're aware, you have a difference of cubes. It's equal to the first thing minus the second thing times the first thing squared plus the first thing times the second thing plus the second thing squared. And just to be complete, a sum of cubes also factors in a similar way. A plus b times a squared minus ab plus b squared. The reason we say it's SOAP is because if you look at the sign here, then the sign here is the same, the opposite, and always positive. So yeah, so yeah, if you really wanted to, you could say that, for example, a to the 5th minus b to the 5th totally does factor as a minus b times, oops, sure, I gotta think about a to the 4th plus a cubed b plus a squared b squared plus ab squared cubed plus b to the 4th. I'm pretty sure that's how that factors minus this. Yeah. I mean, there's a similar, but probably slightly more complicated formula for sum of 2/5 powers, because you probably have to alternate signs. Yeah. Probably, yeah. So the point of this, though, is that if you have a difference of cubes, factors like this. And so what I want you to see, or what we're going to do, is we're going to think of this part here as the A and this part here as the B. And so to make it actually look nice, what we want to happen is we want to multiply this by its conjugate. That is it's not really, the conjugate's the wrong name. Multiply it by the thing so that when you actually multiply it out, you end up with a cubed, which will be x plus h, minus b cubed, which will just be x, and then the x's will cancel and you'll just be left with h on top. So that's what we're going to do. So we're going to multiply by this mess here. Okay, so we're going to have, this is equal to the limit, h goes to 0 of, and I'm going to write things as powers instead of as roots. So we have x plus h to the 1/3 minus x to the 1/3 all over h. We're going to multiply by a squared plus ab plus b squared. So I'm going to multiply by a squared, so x plus h to the 2/3 plus ab, which is x plus h to the 1/3 times x to the 1/3 plus b squared, which is x to the 2/3 over the same thing. Okay. And I guess I will show the work of multiplying it out, even though you should know what happens here. So let's see what happens. So wow, draw a straight line, James. So on the bottom, we're just going to leave it as is. H times all this stuff, because eventually we're hoping that h cancels out. You don't want to multiply by 3. You're going to cancel that. So you've got x plus h to the 2/3 plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. Okay, on top, let us actually do the work of distributing it. So let's actually, this times that, That's going to give you an x plus h to the 3/3, which is just x plus h. And then this times this is going to give us an x plus h to the 2/3 times an x to the 1/3. And then times that. You're going to get x plus h to the 1/3 times x to the 2/3. And then we do the other ones. This times this, you're going to get minus x to the 1/3 times x plus h to the 2/3. And then minus x to the 2/3 times x plus h to the 1/3. And finally, minus x to the 1/3 times x to the 2/3 is just x to the 3/3. And look at what cancels. Everything except for the first and last term. This x plus h to the 2/3 times x to the 1/3 cancels with minus x plus h to the 2/3 times x to the 1/3. And x plus h to the 1/3 times x to the 2/3 cancels with minus x to 2/3 times x plus h to the 1/3. A lot of words to say. So that's why I multiplied by that. So that then look what we're left with. X plus h minus x. Oh, the x's cancel as well. H divided by h is 1. So we're left with the limit h goes to 0 of 1 over x plus h to the 2/3 plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. And that's going to equal 1 over x to the 2/3 plus x to the 1/3 times x to the 1/3 plus x to the 2/3, which is finally equal to 1 over 3 times x to the 2/3. Or if you prefer, 1/3 times x to the negative 2/3. Exactly what the power rule would tell us we would get. So that is essentially the same process you would use for doing something like this. So if I wanted to do this limit the long way, even though I don't really want to do it because we just kind of did it, the work we would do is to say, well, sorry, I want to like make it so you can see both things. So if I was trying to deal with this limit here, even though it's totally heinous, what I would multiply by is, let's see. So again, I'm thinking of this as my A and this is my B. So I'm going to multiply by a squared plus AB plus B squared. So that's going to be the cube root of 125 plus h squared plus 5 times the cube root of 125 plus h plus 5 squared, all over the same thing. So if you really had a desire to do this the long way, this is how you would do it. Again, it's not the point of the problem, but it is good to know that it is doable even this other way. Which I guess we could do if you really want to. Okay. We can. I'm not, it's really fine. Like, even powers, yeah, that should be, I mean, again, I don't want to use the word conjugate because conjugate specifically refers to the same quantity with a minus sign in front of it. Right, because, well, I mean, are you talking about even powers or even roots?
Even powers. If you have e to the power of 4 minus b to the power of 4, and you want to, oh, sorry, 1 over 4. If you have a to the power of 1 over 4 minus b to the power of 1 over 4, so even roots.
Sure.
And we're trying to conjugate it. Would that be exactly the conjugate, just the power of 2, or would it be some other number?
No, so I mean, you're trying. So the whole idea is you're trying to get back to just your quantity without like the power. So if you were trying to find, for example, if I had my function was the 4th root of x, and I wanted to find the derivative. So it's going to be the limit as h goes to 0 of x to the x plus h to the 1/4 minus x to the 1/4 all over h. I need to get back to having, so what I'm trying to reconstitute here is something to the 4th power minus something to the 4th power. Because I want to get rid of that 1/4 power, and the way to get rid of it is by having a 4th power. So what I'm thinking about is, oh, I'm thinking about the fact that I want to eventually get a to the fourth minus b to the fourth, where my a is x plus h to the 1/4 power, and my b is x to the 1/4 power. So then I'm thinking about, well, how does this factor? Well, that factors as the difference of squares, a squared minus b squared times a squared plus b squared. And this factors further as a difference of squares, a minus b times a plus b times a squared plus b squared. So what I would have to multiply by would be this stuff here. I would need to multiply by a plus b times a squared plus b squared over a plus b times a squared plus b squared. So if I was trying to deal with this, I would end up multiplying it by x plus h to the 1/4 minus plus x to the 1/4 times x plus h to the 1/4 squared. So x plus h to the 2/4 plus x to the 2/4, which I know simplifies to 1/2, but I'm not worrying about that. So this is the thing that you would need to multiply by to actually do this definition of the derivative the long way. This is why we eventually develop the power rule, so that we don't have to do this crap every time we're trying to find a derivative, right? Because it gets super duper just terrible to do. You can totally multiply this out, and the top is definitely going to multiply out to the thing you want. So actually, fine, we'll finish this one because I've already started, I've already done most of it. So, but just so here's the thing though, I'm not going to do the stupid thing I did last time and actually multiply out the top, because the whole reason I did this thing is here is because I know that if I multiply a minus b times a plus b times a squared plus b squared, I know that that multiplies out to a to the 4th minus b to the 4th. So this is going to end up equaling the limit as h goes to 0 of a to the 4th minus b to the 4th, all over all that trash. So I'm not going to multiply out. X plus h to the 1/4 plus x to the 1/4 times x plus h to the 1/2 plus x to the 1/2. And then simplifying this, this is going to be the limit as h goes to 0 of x plus h minus x, all over all the same garbage on the bottom. So much garbage. Don't worry, we're almost done. But I told you not to write it down. It's all okay, so then x is cancel. H divided by h is 1. So the limit h goes to 0 of 1 over all this leftover stuff. X plus h to the 1/4 plus x to the 1/4 times x plus h to the 1/2 plus x to the 1/2. And then finally, we let the h's go to 0 and we're left with 1 over x to the 1/4 plus x to the 1/4 times x to the 1/2 plus x to the 1/2, which is equal to, hopefully, gosh, I hope I did this right. Okay, so we've got 1 over 2x to the 1/4 times 2x to the 1/2, which is equal to 1 over 4 times 1/4 plus 1/2 is 3/4. And that is exactly 1/4 x to the negative 3/4 power, as it should be if you're taking the derivative of x to the 1/4 using the power rule. So it works. It's a giant pain in the butt, but it works. So that's why we use the power rule, right? Because you don't want to do this over and over again. You could always do it, right? It's always possible to calculate. It's just gets grosser and grosser and grosser the rootier your roots are.
I imagine there's a proof for the nth roots, right? The same way that we do.
Yeah, I imagine there is. I have never actually seen it, so I imagine there is, but I don't actually know. It's probably not an easy proof, right? It's probably, but there's probably some sort of way of generalizing this. But we typically just avoid and say, yeah, it works, and move on. We've seen it work for 2 terrible powers. We're gonna assume it works for the rest of them, so we're good to go. Other questions about this particular thing? All right, let's see here. All right. So let's talk about, let's actually look at this. Yeah. So we're going to let capital H of X equal the product of f of X and g of X. And we're going to find H prime of X. We're going to find the derivative. So we're gonna prove the product rule right now because it's worth proving. It's good to see that it actually works and it's not just like some magical formula. So we're going to write this as, well, I want to find H prime of X, which is the limit H little, I don't know, H maybe wasn't the best choice. Little h goes to 0 of capital H of X plus little h minus capital H of X over H. Usual limit definition. So whenever someone says find the derivative of a thing and we don't know how to do it, we kind of fall back on, let's look at the limit definition. And I know, right? This is a very like, it's not even really a thing. It's just like some product of two whatever functions. But we're still falling back on the definition. So what we're going to do is we're going to rewrite each of these in terms of f and g. So h of x plus h is, well, h of x is just f of x times g of x. So h of stuff, excuse me, is just f of stuff times g of stuff. And h of x is just f of x times g of x. Now here's where things get a little bit tricky. We're going to add and subtract something to make it look like we want it to look like, but it's going to not change it at all. So here's what we're going to do. We're going to rewrite this as the limit as h goes to 0 of, oh, cool, thank you. F of x plus h times g of x plus h. Leave yourself some space. Minus f of x times g of x. And now we're going to add and subtract the same thing. So we're going to subtract off. Which way do we do it here? Oh yeah, f of x times that, right? F of x times g of x plus h. And we're going to add back the same thing. F of x times g of x plus h. We didn't change it. Still the same. But now we're going to group things together in a very specific way. So I'm going to break this up into two fractions. The limit as h goes to 0 of f of x plus h times g. I might as well even factor out the g of x plus h minus f of x times g of x plus h all over h. Those are the first two terms with the g of x plus h factored out, plus the next two terms with the f of x factored out. So g of x plus h minus g of x all over h. Still the same? Still the same. And now we're going to make it look just a tiny bit different. And actually, so here is where we often use some of the limit rules that we have talked about a lot, but never really used. We're going to say that the limit of the sum is the sum of the limits. This is equal to the limit as h goes to 0 of, I'm going to rewrite this as f of x plus h minus f of x all over h times g of x plus h plus the limit as h goes to 0 of f of x times g of x plus h minus g of x all over h. And now let me ask you all a question. If I look at just that for a second, what's another name for the limit as h goes to 0 of f of x plus h minus f of x all over h? The derivative of the function f, right? That's literally the limit definition of f. So this right here is just f prime of x. Let me back up because I just came back to them. So all we did here was we took this expression here, the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. And we added and subtracted something that we knew was going to be helpful. We subtracted f of x times g of x plus h, and we added f of x times g of x plus h. And then we broke it up into two pieces, and then we factored out the thing we wanted. And the reason we knew we wanted this is because we said, oh, that looks like it's the limit definition of the derivative. So that's definitely f prime of x. And in a similar way, the limit as h goes to 0 of g of x plus h minus g of x all over h is going to be g prime of x. And as h goes to 0, g of x plus h is going to go to g of x plus 0. And as f of x, well, as h goes to 0, f of x doesn't change. F of x is still f of x. So look what we end up with. We end up with f prime of x times g of x plus f of x times g prime of x. And that is what is known as the product rule. So let me write this down. Here, let me zoom back out. So a couple different ways to write this. I usually like to write it as the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. And I'll just point out that people get a little bit loose about the way they write this because the order of addition and multiplication doesn't matter. So people often write this as f prime of x times g of x plus g prime of x times f of x. Right? Also totally fine. People, I always kind of think of it, whenever you have the derivative of a product of things, it's the derivative of one piece times the not derivative of the other piece, plus, and then you switch it up. You do the derivative of the other piece times the not derivative of the first piece. So it's always one derivative and one not derivative. For two pieces. And then to be more compact about it, people just kind of write like f times g prime equals f prime g plus f g prime. That's kind of the easiest way to write it. So we can then use this to take derivatives of things multiplied together. Now at this point, a lot of the things we have to take derivatives of are just things you can multiply out anyway. Right? Like I don't have a lot of examples currently because most of the functions we've differentiated so far are just power with that. So for example, just to point out, let's see that the power rule really does work to take the derivative of x to the fourth times x to the third. So yes, I know one way we could do it is just by multiplying it out. You can say, oh, well, James, you should listen to your own device and say that's the derivative of x to the seventh, which is equal to 7x to the sixth. And I think, yes, of course, that's true. But then let's actually do it the other way. So let's actually use the product rule and say the derivative of x to the fourth times x to the third is equal to the derivative of x to the fourth times the not derivative of x to the third plus x to the fourth times the derivative of x to the third, which is going to be 4x cubed times x to the third plus x to the fourth times 3x squared, which is 4 times x to the sixth plus 3 times x to the sixth, which is indeed 7x to the sixth, as it should be. So something to be super duper aware of is that when you take the derivative of a product, it's not just the product of the derivatives. Right? It is certainly not true, right? If I was to try and do this, but not paying this way, we can't find the derivative of x to the fourth times x to the third by just saying 4x cubed times 3x squared. Right? That is definitely not true because that's equal to 12x to the fifth, which we know is not the derivative of x to the seventh. Later on, we will talk about, yeah, in fact, let's look at a couple more examples. So I'll just say, eventually we will use product rule to differentiate things like f of x equal to x to the fourth times sine of x. But to be able to do that, we're going to have to know what the derivative of sine of x is first. I think it's time for a bathroom break because I need to use the bathroom. So let's take a few minutes break. Sorry, you all. I know I haven't been taking a break because I just keep talking, but today I have to pee, so take a break. You're welcome to go to the restroom as well. Have a minute to think about whatever, think of questions you might have. Just a second. Yeah. All right, let's keep going in this direction for a little bit. We'll spend like maybe the last 20 or 30 minutes talking about limits to infinity. I kind of want like try and straddle the difference, right? I know some people are way ahead, some people are way, I won't say behind, but like some classes are moving at a much faster pace, some classes are moving at a much more, in my opinion, reasonable pace. So let's go ahead and look at a couple more things here, and then we will kind of circle back around to some limits. So let's look at the following. Suppose I wanted to find the derivative of something like x cubed plus 2x times x to the 7th power plus 9. I could multiply it out, and I probably would multiply it in general, but we could also use the product rule. So if I want to use the product rule, I can say, well, that's going to be equal to the derivative of the first thing. And I do like to, at least when I'm getting used to using the product rule, I really like to write it out as the derivative of the first thing, not actually finding the derivative of the first thing, but just writing it out as first thing prime times the not derivative of the second thing. And then we switch it up. We leave the first thing alone. We multiply by the derivative of the second thing. And then we actually find those things. So then the derivative of x cubed plus 2x is 3x squared plus 2. And x to the 7 plus 9 is x to the 7 plus 9. And then the other thing is x cubed plus 2x times the derivative of x to the 7th is 7x to the 6th. And then we could simplify it. And the reason we're really doing this is kind of just to really verify to ourselves that no matter which way you do it, as long as you're correctly applying the rules, you should get the same answer. So if we simplify this, which is kind of gross, let's see, we get 3x to the 9th plus 27x squared plus 2x to the 7th plus 18 plus 7x to the 6 times x to the 3rd is 7x to the 9th plus 7 times 2 is 14x to the 7th. And then combining like terms, I should use equal signs here. We get 10x to the 9th. And then we have a 16x to the 7th. And then we have that. And we still have a 27x squared and 18. Versus if we multiplied it out first, the derivative of x cubed plus 2x times x to the 7th plus 9 should equal the derivative of x to the 10th plus 2x times x to the 7th is 2x to the 8th. X cubed times 9 is 9x cubed. And 2x times 9 is 18x. And we can see, oh yeah, the derivative of that is exactly what we got right there. Because we're going to get 10x to the 9th plus 8 times 2 is 16x to the 7th plus 9 times 3 is 27x squared plus the derivative of 18x is 18. Same exact answer. So the product rule really does work. It does what we think it's supposed to do. Yeah.
Plus or minus.
I wouldn't quite say that, but I mean, yes, we. No. Well, we're doing, so the thing we're doing is we're kind of, in some sense, we know what we're trying to get to already. So some of this is, someone has seen this before and said, well, okay, I know what I'm looking for. Right, we did this whole thing where we said, I have this, and then since I know that I'm looking to try and get f prime g plus fg prime, I'm trying to subtract and add a thing so that I can get my f of x plus h minus f of x all over h, right? I'm looking to make that f prime show up. So totally, yeah. And you'll see later on, there's a lot of that reverse engineering where like in 21b, when we find like the integral of secant, for example, really it's well, someone did a whole bunch of other work to find this nice answer, and then if you reverse engineer the nice answer, there's a really kind of easy way to get there by just doing a multiply by this over this. But really, the long route is much more complicated. Kind of it's actually really integral of secant has to do with maps and like projecting like maps onto 2 dimensions, which is like kind of neat, but not important for now. Or later either. Yeah, I'm gonna throw a quotient rule at you and then one derivative of a trig function, and then we will backtrack. So let's see here. Where'd you go for that? I should know. So the nice thing about the quotient rule, in my opinion, is it's very similar to the product rule. So if I want to find the derivative of f of x over g of x, we can do the same sort of thing. We can write this. Oh, we can do it that way too. That's kind of tricky. I didn't even think about that. I never do it that way though. I'm going to write it as the limit h goes to 0 of f of x plus h or g of x plus h minus f x over g of x. I don't know why I use brackets there. It's totally unnecessary. Thought I was going to need them, but I didn't. It's okay. It doesn't hurt anything. Right? No one's hurt by brackets. Okay, so then we want to subtract these things together. So I'm going to do the common denominator, and I'm also going to write instead of dividing by h, multiplying by 1. So I'm going to write this as the limit as h goes to 0 of, I'm going to multiply this by g of x over g of x minus, I'm going to multiply f of x over g of x by g of x plus h over g of x plus h. Finally, all this is divided by h or multiplied by 1 over h. Okay, so let's see what we've got here. I'm going to rewrite this as the limit as h goes to 0 of f of x plus h times g of x. I'm going to leave myself some space. I'm going to have a minus f of x times g of x plus h over here. And the denominator, I have my h times g of x plus h times g of x. And just like before, I'm going to add and subtract something in there that's going to make it so things look like what I'm looking for. I'm looking for a derivative of f times g minus f times the derivative of g. So I'm looking for the derivative of f. I want an f of x plus h minus an f of x times g of x. Right? This here, when I factor out the g of x, I'm left with f of x plus h minus f of x over an h, which is the derivative of f. But then if I subtract f of x, g of x, I have to add it back in. Now, again, I should mention, no one's going to ever ask you to do that, right? I think it's important for you to see it because it's important for you to actually know where these rules are coming from. Like, someone told me this rule, it works, but like, I don't really know why. This is really why. And we're taking the derivative of this quotient and we're just doing some algebra to eventually get to actual limits that are derivatives that we recognize. So we're going to break this up into some convenient pieces here. So I'm going to pull this denominator kind of out from this expression. This is where the algebra just gets a little messy. So I want to pull this 1 over g of x plus h times g of x out in front. Also, if you've ever seen the quotient rule before, you know that we end up with division by the bottom thing squared. So that's looking pretty good because when h goes to 0, you're going to have a g of x times a g of x, which is a g of x quantity squared. So things are looking like they're moving in the right direction. Question? No. Sorry. I thought you're like, sure, totally. So then I'm going to think of these two first pieces together. These two first pieces I can factor out a g of x. So I'm going to write these first two pieces of the following, right, as f of x plus h minus f of x all over h times the g of x. And I want to point out that this here is the same as f of x plus h times g of x minus f of x times g of x all over h times g of x plus h times g of x. Just doing a lot of simplifying at once here. And then over here, I'm going to actually do something extra special. I'm going to change the order of subtraction. So I'm going to say it's going to be minus, instead of g of x minus g of x plus h, I'm going to have g of x plus h minus g of x. Times f of x. Anything I can explain in more detail here. So I'll point out before there are questions, just I'll point out, right? We could totally write this as one big fraction, right? So if I wrote this as one big fraction, the denominator would be h, and the top would be f of x plus h times g of x minus f of x times g of x. Cool, that's up right there. And then minus g of x plus h times f of x, that's that part there. Minus, so plus g of x times f of x, which is that part there. And we'd also have g of x plus h times g of x in the denominator. So totally the same. All right. But now here's the cool part. The limit of this goes to f prime of x as h goes to 0. And the limit of this goes to g prime of x as h goes to 0. And just to be super duper extra explicit, this goes to g of x as h goes to 0. So technically, if you wanted to be very precise about this, you would break this up and you would say, okay, this is going to equal the limit of this times the limit of all this. And then the limit of all this would be the limit of this times the limit of this minus the limit of this times the limit of this. But we're not going to write all that because it's terrible. We're just saying, like, we know these limit rules work. You can essentially kind of distribute the limit across addition and multiplication. And so we're just going to be like, okay, we get the thing. We get 1 over g of x times g of x times f prime of x times g of x minus g prime of x times f of x, which people prefer to write as f prime of x, g of x minus f of x times g prime of x is how most people like to write it, all over g of x quantity squared. That's your quotient rule. So just to write it out again, so that you can see it not all in this long ass thing, you have the derivative of f divided by g is f prime g minus f g prime all over g squared. People use a mnemonic device for this. People like to say that if you have high over low, derivative of that is low d high, where d means derivative of. So bottom thing times the derivative of the top minus top derivative of the bottom, or high d low all over low squared. To me, that's never caught on. I will tell you literally the words that I say in my brain, which is kind of lengthy, but whatever. As I say, the derivative of the top over the bottom is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's just the way I say it in my head. Bottom to the top minus top to the bottom, all the bottom squared. Now, the thing I want to point out is that what's kind of nice about this is if you look at this way of writing it specifically, it's very evocative of the product rule. The product rule, I'll remind you again, the derivative of f times g is f prime g plus f g prime. Say that one more time. Like use both rules at once? Oh yeah, all the time. Yeah, so shortly here we'll get to a place where I have, I think, a fairly extensive handout about all these kind of different practice problems where you're having to use the product rule, the power rule, the chain rule, the quotient rule, all kind of together at once. Let me. It's not. It's just applying the rules in the correct order.
So, my professor yesterday specifically said we're not doing any like solving of them. She basically was like, we're proving all of them. So does that just mean we're just doing this?
I don't know exactly what she means by that. If we're just proving, like
She basically was
like she's never gonna make you do like a product rule question or a quotient rule question.
That was for high school. Now we're gonna like prove all.
Who's your professor? I don't know them.
And she like yesterday was the most like confusing thing like I've ever like, and I just was like, I'll go over her notes again and it's not there. And I just.
So yesterday you guys talked about the product rule and the quotient rule.
We talked about this kind of stuff.
Okay.
Right? But
She didn't give you any examples.
no, we're just gonna prove everything.
Right, because in her opinion, now that you've seen this, now that you've seen how to do it, well, obviously every other example should be fine. I'm saying this sarcastically, right? Like, I don't think that's true. I think that is kind of BS. People need to practice this stuff besides just seeing like how the rule works. So what I would say is, I would actually encourage you, like, so I assume you have homework, but I don't have to know.
Okay, so yeah, that's another thing. So like the homework is actually solving them with like
Right,
variable questions,
right.
all that stuff. But like in class, she just basically said like, we're not doing that. We're just doing like proving it. So like, I guess if the proof is that is what we do.
Yeah, totally. And there's other ways of proving this. Like, this is one way of doing it.
So like.
You're right. Maybe class isn't very helpful, which is unfortunate, but
But when she says prove, it's what you're.
yeah, this is a quote unquote proof.
Okay.
I have proved the quotient rule by showing you that if I start with the derivative of a quotient of any two functions, I can get to the fact that that derivative of that quotient is equal to the derivative of the top thing times the derivative times the bottom thing minus the top times the bottom of 1 squared. Right? I proved it.
Not just
Right. Right. So let's do an example. So like I'm going to apply the quotient rule to an example. Like for example, we could be asked to find the derivative of x to the fourth plus x over x cubed minus 1. I don't love x to the fourth plus x. Let's make it x to the fourth plus x plus 2. I didn't love x to the fourth plus x because I could have factored out an x. I don't really want to do that. So, okay, so I'm just going to use the rule where the rule says it's going to be, I'm going to say it the way I say it in my head, which is the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And if no one has asked you to simplify it, we can simplify this. And the thing is, most of the time for these kinds of things, they get ugly pretty fast. And usually people are not asking to simplify these things. But if we want to simplify this, we could. It's kind of terrible. X cubed times 4x cubed is 4x to the 6th. X cubed times 1 is x cubed. Minus 4x cubed. Minus 1. Minus, and then each of these things get multiplied by 3x squared. So you have a minus 3x to the 6th, a minus 3x cubed, and a minus 6x squared. I don't want to multiply at the bottom because it's usually considered more simplified just to leave it like that. And then if we simplify this even further, let's see, 4x cubed minus, those really, thank you. Yeah, I was like, that doesn't actually cancel. Good call there. 4x to the 6th minus 3x to the 6th is just x to the 6th. Got that, got that. X cubed minus 4x cubed is minus 3x cubed, minus another 3x cubed is minus 6x cubed. And then got that, and then minus 6x squared minus 1 all over x cubed minus 1 squared. But really, you should not multiply out and simplify the numerator unless specifically asked to. So there's one example. And that's kind of what we do. Let's look at another example. Let's say I want to, sure. Problem is I don't have sine and cosine yet. So let's take a look at, see the derivative. In fact, why don't you all try this one on your own? So try finding the derivative of x to the 5th over x to the 4th plus 9. Just using the quotient. And I should ask, has anyone talked about the derivative of e to the x yet?
Yeah.
Yes, we will have. Okay.
That was also extremely confusing, because she proved that too.
Sure.
For that?
Yeah.
Yeah. It was for entire board.
Okay.
Oh my God.
Entire, like, how
Well,
many
no,
boards do
It
you?
has like a little like
Okay. All right.
classes.
Oh, how many people are in your class? Okay.
Everybody.
Is she a grad student? Oh. Okay.
She's like a first-year professor from Europe.
Yeah,
Sure.
it's honestly like.
Is she a professor or is she like a,
Oh,
she's not like a lecturer, like a postdoc or something?
I don't know, but.
Okay.
it's-
All right. It's not important.
it's not.
Yeah. Excuse me. All right. Let's go ahead and do this one. Even.
There's only not a lot of people who just ever just drop the class.
Like switch to another one.
Yeah,
I mean,
but it didn't work with my
Right.
schedule or something.
well, hopefully, maybe have you had a test yet?
Yes,
Terrible.
yes, it was horrible.
Sometimes people who are really maybe not doing an excellent job of teaching, maybe sometimes give relatively easy tests. I thought. So let's look at this one. This is going to be, and I'm just bottom derivative to the top minus top derivative to the bottom all over the bottom squared. That's it. Done. Okay, yeah.
So that would be like the proof of like.
I wouldn't call this not a proof. I'm just using the quotient rule to calculate this derivative. Yeah. So when someone says the word proof, what they kind of really mean is show something is true very generally. So I do think, yeah, I think let's go ahead and talk about two more things. Yeah. So first of all, I do want, so we're not going to get fully into the trig derivatives right now, but I do want to show you one trig derivative. I'm going to show you in two different ways that the derivative of sine of x, well, in fact, before I even tell you what the answer is, let me show you the nice, easy way of doing it. Or at least the nice, I wouldn't say this is not a proof. This is a justification that is a little hand wavy, but it's totally fine. Because the point is not to maybe prove it necessarily, it's to understand what's happening. So I'm going to graph sine of x. I'm going to give myself enough room to graph something below it as well. Okay, so let's see, 2 pi is maybe about there. There's pi over 2, 3 pi over 2. And we know that sine starts at 0, and then sine of pi over 2 is 1. Sine of pi is 0, and sine of 3 pi over 2 is -1, and sine of 2 pi is 0. And sine has this very nice periodic nature, just keeps doing the same thing forever and ever and ever. So now, here's where it's really, really good to think about the fact that if you want to find the derivative of a function, one way to think about a derivative, it's not the only way to think about a derivative, but one way to think about a derivative of a thing is the slope of its tangent line. So looking at specifically, in fact, let me make sure this looks good here. Pi over 2, pi, pi over 2, 2 pi, 1, -1. So if I look at pi over 2, first of all, I look at the tangent line. What's the slope of the tangent line? 0. It's a horizontal line, slope is 0. So that means the derivative is going to have a value of 0. And looking at 3 pi over 2, picking the easy points first, 3 pi over 2, the slope is also 0. Okay, now looking at 0, slope of that tangent line, if I draw it good, which I didn't, but okay. The slope of that line looks like it's about how much? Yeah, that kind of looks like the line y equals x. So it looks like the slope of the tangent line could potentially be 1. And by the symmetry of the sine function, right? The slope here and the slope here should be negatives of each other. And the slope of the tangent line here is definitely -1. Yes, that tangent line does go through the function, which is kind of weird, but sometimes tangent lines do that. And I kind of drew this one poorly. That tangent line really should actually go through the function. It's not important, like, but I do want to not draw the wrong thing. So technically right here, the tangent line does actually go through the function, which is kind of bonkers, but it does do that. And here the tangent line has a slope of 1. So if I try and graph this function here, what friendly trigonometric function does this look like? Oh, it looks like cosine. So that's the first way I like to think about the derivative of sine. Is if you just graph the slopes of the tangent lines, you get cosine, which is great. And then I'm not going to do it, but if you did do it, if you took cosine and graphed the slopes of the tangent lines, 0, -1, 0, 1, 0, you would get the flip of sine, which is negative sine. The derivative of cosine is negative sine. We're not going to get too into that today, but I do want to show you the other way of finding the derivative of sine because I do think it's worthwhile. So again, here's a proof that you probably don't need to write down, but you certainly are welcome to. I would never stop anyone from writing notes. Just want to say you don't have to write it. So if I want to find the derivative of sine of x, yes, I can. My go-to, if I don't know how to find the derivative and I don't know any other method, is back to the limit definition. So I'm going to do the limit h goes to 0 of sine of x plus h minus sine of x all over h. And here is where you have to use the angle sum formula to be able to do anything here. So just as a reminder, I know it's everyone's not my favorite formula, to be perfectly honest. Ones I have a hard time remembering. Sine of a plus b is sine a cosine b plus cosine a sine b. And if it's subtraction here, it's subtraction here. And just to be complete, cosine of a plus b is cosine a times cosine b minus sine a times sine b. And then if it's subtraction here, it's addition here. So those are your angle sum formulas. So we're going to use this first one, that sine of x plus h is going to equal sine of x times cosine of h plus cosine of x times sine of h. And we still have the minus sine of x all over h. Okay, so then what do we do with that? Well, this is where things, again, a lot of this is somebody worked it out once upon a time, and then they kind of figured out, well, okay, now we know where we need to go to make it. So what we're going to do is we know where we're going. I know that eventually I'm trying to get to cosine of x. So I'm going to do the only thing I really can do, which is group the things that have the same term together, meaning both of these terms have a sine of x. So I'm going to pull those apart. together, I should say. Pull them together. So I'm gonna write this limit as h goes to 0 of sine of x times cosine of h minus sine of x all over h plus the other piece, cosine of x times sine of h all over h. And I notice something. I notice I've got a sine of h over h, and h is going to where? 0. I know the limit as h goes to 0 of sine of h over h is, right? That's the thing we've seen a few times. If you have something going to 0 and sine of the something over the same something, that limit is 1. So great, we know that that's going to go to 1, and you're going to be left with cosine of x times 1, which is cosine of x. Now, what about this junk over here? Well, we're going to do the following. We're going to rewrite this as limit as h goes to 0. I'm going to factor out the sine of x. And I'm left with a cosine of h minus 1 all over h plus, and I will write this as cosine of x times sine of h over h. And just to be extra explicit about it, I'm actually going to write the limit rules. I'm going to write this is equal to sine of x doesn't care what h is doing times the limit as h goes to 0 of cosine of h minus 1 over h plus cosine of x doesn't care what h is doing times the limit as h goes to 0 of sine of h over h. Cool. So then this is equal to sine of x times, we've seen this limit a few times before, it's equal to 0. I can show you as well, but it's equal to 0. In fact, I will show you. And then cosine of x times this limit is 1. So we end up getting exactly what we thought we should get. The derivative of sine of x is indeed equal to cosine of x. And just so everyone's totally cool with what we did there, let me just point out that this limit here of cosine h minus h, cosine h minus 1 over h being equal to 0, that's because if we multiply by the conjugate, things are going to work out. So we multiply by the conjugate, we multiply it out, we get the limit as h goes to 0, we get cosine squared h minus 1 all over h times cosine of h plus 1. That's almost a trig identity. I mean, it is a trig identity, but it's almost one we recognize. What's cosine squared h minus 1? Almost. It's almost sine squared h. It's negative sine squared because we know that 1 minus cosine squared h is equal to sine squared h. And we multiply everything by negative 1 plus cosine squared h equals negative sine squared of h. So then this is equal to the limit as h goes to 0 of negative sine squared of h over h times cosine of h plus 1. And then we can break this up into the limit as h goes to 0 of sine of h over h times negative sine of h over cosine of h plus 1. That totally multiplies out to be this. Sine times negative sine is negative sine squared. H times cosine h plus 1 is h times cosine h plus 1. And then the limit of this part is 1. The limit of this part is sine of 0 over cosine of 0 plus 1, which is 1 times 0 over 2, which is 1 times 0, which is 0. So it is indeed 0, like we said it was. I really wanted you to do it. So there we go. Okay, so now we have a trig function whose derivative we know, which is great, because then you can do really fun things like the product rule. For example, we could take the derivative of x to the 6th times sine of x. And using the product rule, so often when people use the product rule, they like to write out something like they like, this is my g. When I find the product rule, it's going to be f prime times g plus g prime times f. So let's see, my f prime is 6x to the 5th. My g is just sine of x, right? You leave one piece alone every time. And then plus, flip it up. G prime is cosine of x. F is x to the 6th. I probably would have written this in not that order, but I have to write it in that order. So I would probably actually write this as 6x to the 5th sine of x plus x to the 6 cosine of x. And there really isn't any meaningful simplification you can do there. If you really wanted to, you can factor out next to the fifth. It's not worth your time to do that. You can also then start having things where you have like a product rule inside of a quotient rule. For example, if I wanted to find the derivative of x to the third times sine of x over x to the fifth plus 8. Now I have to use both. And you have to be careful about kind of which order they get applied in. So I see a top over a bottom. So I'm going to take the derivative as the bottom times the derivative of the top. And I'm just going to write out x cubed times sine of x prime. I don't want to do all the work at once because maybe it just feels like a lot to take on at once. And we change it. We did the bottom times derivative of the top. Now we're going to do the top times the derivative of the bottom. All divided by the bottom squared. Now we can't just leave it like that because there are things that say you need to actually take the derivative of this. We actually have to go and take the derivative now. So then we're going to write this as x to the fifth plus 8 times, and now we're going to use the product rule to take the derivative of x cubed times sine of x. So it's the derivative of x cubed times the not derivative of sine plus the not derivative of x cubed times the derivative of sine minus x cubed times sine of x times the derivative of x to the fifth plus 8 is 5x to the fourth. It's a good idea to put parentheses around things, but if you only have one term, you don't have to. Like it would totally be fine if I wrote parentheses there, but it's not necessary for just one. But if you have two things added together, you definitely need parentheses around them to indicate the multiplication spring. All divided by x to the fifth plus 8 squared. And no one should be asking you to simplify this, right? I mean, it's not like totally ridiculous, but there's no point, right? There's no good reason to simplify this other than showing that you know how to multiply things out together. All right, I think I lied about the limits. I don't think we're sorry. I know I said limits a few times, but like sometimes you go in one direction versus the other. So to that end, let's also clarify another thing. The thing I will say, the upside of working ahead as far as working behind is at least these are things you're going to see. So I apologize, like I will just make a blanket apology. I'm not gonna be able to please everyone. I'm sorry. Sometimes we're gonna go one way, sometimes we're gonna go another way. And the problem is there's like 8 different 21A classes and they're all in different places. Speaking of which, next quarter, there will be I don't think it's an actual class you can register for because it's going to be a workshop, but there's going to be a 21B workshop. It'll be, what time is it going to be at? I think it's going to be Monday, Wednesday, Friday at 10, I believe. So it's either let me just check real quick here, just so I can tell you all with authority before I start getting, just so you can plan accordingly if you want to take it. Let's see, let me grab where's the little dots? I need the dots. It is top end, which, you know, plus or minus, good thing, bad thing. Oh my gosh, if I log in, holy crap. I just wanted to tell you guys when a thing is. Okay, do it. Let me in. Sorry, I just want let's see. Where's the winter quarter? Oh, there we go. Just disappeared. Gosh, why? Sorry. Oh my God. Being especially challenging here. One moment. Okay. Let's see. Okay. And the time will be, drumroll please, from 1 to 2. Yeah. Monday, Wednesday, Friday, 1 to 2. Yeah, so the only difference is really like if you happen to have actually registered for this class this quarter to get 1 unit, I don't believe that will be an option next quarter. I mean, technically, I guess that's an accurate statement. There's no actual Co-21B class. There's a Co-21B workshop. It's still going to be the same.
So.
Right. You could totally never come or come whenever you want. Like, I will still take attendance because we still like keep track of the students we serve. But you're right. There'll be no like basis for a grade because no one will be actually enrolled. So you won't have to like, I mean, I hope you'll all still come participate. Like, right. You don't have to ever come. Participate. What's that? Monday, Wednesday, Friday, 1 to 2. In here. No, in here. Well, yeah. Well, but 1 hour 3 times a week instead of 2 hours 2 times a week.
You just have to make sure our classes when you
Right. So I believe we have picked a time that doesn't overlap with any of the 21B classes, but even if it does, it only overlaps with one of them. So there's a lot of options. That is a matter of opinion. Some people think yes, people think no. I mean, like I personally find 21D to be the most challenging personally. But that's also just because I haven't looked at it as much lately. I would say the hard thing about 21B, and I know we're getting ahead of ourselves, but the hard thing about that class specifically is with differentiation. After you've learned all the rules, you can apply the rules. Like, okay, two things are multiplied together. I'm going to use the product rule. Or I have two things multiplied together over another thing. I'm use the quotient rule and the product rule. Or I have a chain rule, right? The rules are very much just like you look at the thing and once you know rules to use, you apply them and they work. Whereas with anti-differentiation, it is not always super duper clear what path is the right thing to do. You might do integration by parts. You might do a use substitution. You might do either one, right? Sometimes there's more than one thing that works. So that's, to me, the hard part about 21B, or one of the hard parts about 21B, is learning how to determine which method of integration is the right one to try first. And then if it doesn't work, to try something else. It's not always clear which path. So that is an argument for why it might be quote unquote the worst, but it's still pretty fun. I mean, from my perspective, because I really enjoy it all. So before we end up here, I did want to show you, just because it sounded like it was giving you some trouble, how we prove that the derivative of e to the x is equal to e to the x. And there's a number of ways of doing this, depending on what you've already got. Some people like to do the derivative of the natural log of x first, and then use implicit differentiation to do this, which is not what we're going to do. So we're going to use limit definition. And this does require one thing. You have to know the following limit. We have to know that the limit as, there's like 1,000 ways I could write it. The limit as n goes to infinity of 1 plus 1 over n to the nth power is equal to e. That's a well-known limit. There's a whole kind of example as if I lend you $1, like, so you can think of this as like the compound interest formula. That formula there, where if I lend you $1 and I charge you 100% interest and I compound it any number of times I want for 1 year, my formula becomes 1 plus 1 over n to the nth power. And if you start letting n be larger and larger values, you'll see that, like, so if I just compound interest once, you're going to owe me $2 at the end of the year. The dollar I lent you plus 100% interest. If I compound interest twice, you're going to owe me $2.25 because I'll earn 50% of the interest halfway through, cents, and then another half the interest on the $1.50 I already have, and half of the $1.50, 75 cents, 25. The point is that as n gets larger and larger and larger, and I do encourage you all to like graph this sometime or something, you will see that the values do get closer and closer and closer to approximately 2.71828, aka E. So the reason I point this out is because I'm going to change this up a little bit. I got time. I'm going to let, this is where things are a little funky. I'm going to let h equal 1 over n. I wish my h's and my n's looked a little bit more different, but that's just my penmanship. So let me ask you all, if n is getting infinitely large, what's happening to 1 over n? Right, going to 0. So I could rewrite this as the limit, instead of n going to infinity, h going to 0. Same idea. And instead of 1 plus 1 over n, I have 1 plus h. And instead of to the power of n, well, if h is equal to 1 over n, then 1 over h is equal to n. So that this is to the power of 1 over h. And that limit is the same. We're going to use that. It's just like a substitution, really. I'm just substituting in h equal to 1 over n or n equal to 1 over h, whichever way you want to think of it. So back here, this derivative is equal to the limit as h goes to 0 of e to the x plus h minus e to the x all over h. We're going to rewrite this as the limit as h goes to 0 of e to the x times e to the h minus e to the x all over h. And then we're going to rewrite that as the limit as h goes to 0 of e to the x times e to the h minus 1 all over h. And now here's where things get kind of bizarre. We're going to replace e with what it's equal to as a limit. So I just said, I know I didn't like prove this, but I'm using other things from before. It is totally true that e is equal to this limit. Okay, so now here's where I've always had a small problem with what people do here, but it's totally valid. I just don't love it. So this e right here, I'm going to throw in the limit. I'm going to throw in the limit as h goes to 0 of, where'd you go? 1 plus h to the 1 over h. I'm going to put that in for e right there. Okay, so now watch this and watch how I'm going to say something that feels maybe kind of wrong. So e gets replaced with this limit. Okay, now check this out. I didn't write the limit there because it's right there. I don't need to write it twice. Right? Why would I write the limit twice?
So the issue is for n, x to the x. Difference in x. It's the same thing.
Sure.
We can do that.
I'm sorry. I'm not sure. What are you saying
So
exactly?
when you replace n with h, I thought h was just an arbitrary value, but now h is the same exact h as the thing the limit of the compound function on.
Yeah, so I'm just saying that I'm just saying here that right, if n is going to infinity and h is 1 over n, then h is going to 0. I'm not doing anything illegal, I promise. It might feel a little dicey, but it's totally valid. So check this out, and we're almost at the end here. When you have a power to a power, you multiply the powers. 1 over h times h is just 1. So this is equal to the limit as h goes to 0 of 1 plus h minus 1 over h. Don't forget the e to the x out in front. And now 1 minus 1 cancels. H over h is 1. So this is just the limit as h goes to 0 of e to the x. There's no h's left, so great, you get e to the x. So I will admit, this feels moderately hand-wavy, and it might be something different than what your professor actually did. What I'll say is that at the end of the day, well, I'll say typically at the end of the day, no one is asking you to prove this. No one's asking you to prove, typically, no one's asking you to prove that the derivative of e to the x is e to the x. What they want you to know is that the derivative of e to the x is e to the x.